Hello and welcome back to our video lecture series. In this video, we're going to talk about the normal distribution. In particular, recall that the normal distribution is a bell curve distribution that is symmetrical around the midpoint. In a normal distribution, the mean, median, and mode are all at the same value. The standard normal distribution is a workhorse distribution for many of the statistical models we'll be using for the rest of the semester. This will include difference of means testing as well as beta testing for regression analysis. Let's jump into a visualization of normal distribution now.
Okay, so here we have a visualization or a figure of the standard normal distribution. You can see here that because it's a normal distribution, it is symmetrical around the mean and the median, which in the standard normal is set at 0. And we've denoted the standard deviations for the standard normal distribution on the x-axis. Once again, the standard deviation for the normal distribution is 1. So you can see here that we have a mean of 0, a standard deviation of 1, negative 1, negative 2, positive 2, negative 3, positive 3, negative 4, positive 4. The standard deviation does go out to infinity, although so few observations are out past essentially 3 standard deviations that we usually don't represent them in the figure. Looking at the y-axis, you can see that it says density. This refers to the fact that when we look at the normal distribution graphically, we're looking at a cumulative probability density function. Once again, if you kind of remember that PDF's probability density functions, or basically use area under the curve to represent the likelihood of drawing a specific value from that distribution. So because the standard normal distribution is symmetrical, 50% of all observations will be less than the mean. In this case, 50% of observations will be less than 0, and 50% of observations will be greater than 0. Also note here that on the top, it says that there's a 65, 95, 99.7 rule for normal distributions. Basically what this means is that for a normal distribution, 68% of the area is between negative 1 and positive 1 standard deviations from the mean. 95% of observations are between negative 2 and positive 2 standard deviations from the mean. And finally, 99.7% of observations are between negative 3 and positive 3 standard deviations from the mean. This also means that very few observations, really collectively only 0.3% of observations, are going to be out past the negative 3 plus 3 standard deviation marks. So really, we are looking at most of the area or most of the values really between negative 3 plus 3 standard deviations on a standard normal distribution. So here, once again, the standard normal distribution has a mean of 0 and a standard deviation of 1. Naturally, not every variable is going to have a standard normal distribution because other variables are going to have their own means and their own standard deviations. So let's take, for example, a variable that is normally distributed. Let's look at SAT scores. If you look at SAT scores for all test takers, that is, you look at SAT scores for everybody that takes a test in a given year, the average test score is about a 1059 with a standard deviation of 210. So you can see here that I've overlaid the first standard deviation underneath our x-axis on our standard normal distribution graph. In this regard, we know that 1059, that average SAT score, corresponds to 0 on the standard normal distribution because that's our mean. If we subtract a standard deviation, in this case 210, from that mean of 1059, we get 849 for our negative 1 standard deviation position. If we add 1 standard deviation, that is, we're adding 210 to our 1059, we get 1269, which then represents our plus 1 standard deviation from the mean. So we could say then with SAT scores that we would expect 68% of SAT test takers to score between an 849 and a 1269. We can, of course, add in our second standard deviation. So we can take our 849, which puts us at negative 1 standard deviations from the mean, subtract another 210, which brings us to 639 for negative 2 standard deviations below the mean. We can add in 210 to our 1269 plus 1 standard deviations from the mean, which will give us 1479 at our plus 2 standard deviation above the mean point. Now you can see on the graph here that we would expect then that 95% of test takers are going to score between a 639, and a 1479 on the SATs. Finally, we can add in that third standard deviation, which will cover 99.7% of test takers. Here, adding in that -3 standard deviation value, we have 429. That's the 639 at -2 minus another 210. And on the high end, at +3 standard deviations, I put a 1600, although note the asterisk there. If we actually added 210, that would give us 1689, which is above the max score of 1600. So just to keep things consistent with actual values, I put the 1600 there. Although in a theoretical statistical distribution, we could put a 1689 for the +3 standard deviation mark. So in practice, or in real life, 99.9% of students really are covered between that 429 to 1600 score. There might be a handful of students that somehow score below the 429. That would account for the rest of that 100%. So if you've taken the SATs or you've taken really any standardized test, normally what happens when you get your results is you get your actual score, which is the numeric value you got on the exam, and you get your placement essentially on this distribution. Generally, we're talking about the percentage of students who will perform better than on the standardized test. So that means that if you're kind of looking at this graph, if you scored a 1059, we know you are at the mean, which means that 50% of test takers are below you. You would be at the 50th percentile. If you were at the 1479 score, you know that you've scored better than 95% of test takers on the SATs. So the interesting implication for statistical analyses here is to think about statistical significance, which at least in terms of the SATs would mean, did you perform exceptionally well on the SATs or did you perform exceptionally poor on the SATs? Now recall that for statistical significance, we're usually using that 95% benchmark. In other words, to be considered statistically significant or exceptionally different than the average test performer, you would have to be beyond the 2 standard deviation mark. That is, you'd have to be away from 95% of the test takers for the SATs. So here I've overlaid, just to give a visualization of what that might be. To be an exceptionally poor performer then, at the 95% level, you would have to have a score at or below the -2 standard deviation mark or at the +2 or above positive standard deviation mark. Substantively, would call you an exceptionally poor performer. You would have to have a score at 639 or below. That way you would know that basically 95% of test takers are performing above you. Or to be an exceptionally good performer, you would have to be at 1479 or above, knowing then that about 95% of test takers are below you. So once again, you can think about that as statistical significance, being away from 95% of those observations, and the cutoff mark for the standard normal distribution is about the 2 standard deviation mark on both the negative side and on the positive side. So at this point, we've talked a little bit about the standard normal distribution and how to overlay our own normally distributed variable on the standard normal. The last little bit of information we need to cover in this clip is how to take specific values of our variable and locate them on the standard normal distribution. That is, so far we've taken a look at how to overlay the whole values of standard deviations on the standard normal. And that's easy to do by locating our mean value at 0 on the standard normal and then adding the standard deviations to that mean to figure out what the values are for the first standard deviation, the second standard deviation, and the third standard deviation from the mean. But what if we had a specific value? Let's say we took the SATs and we got a score of, let's say, 1300. We can look in kind of our graph that we created and say, well, we know 1300 is going to be between 1 and 2 standard deviations from the mean, but that's really all we could say by the way we've set it up now. So what we really need to do is have a translation function where we can take any specific value from a normally distributed variable and locate it on the standard normal. Once again, if we have that translation function, we can do the reverse as well. If we know where we are on the standard normal, we can always figure out where we are on our variable's distribution. So it turns out that we have a translation function, and that translation function is called a z-score. Z-scores substantively are the number of standard deviations an observation is from the mean. So a z-score is a standard deviation score. That is, a z-score is your position on the standard normal distribution. We can calculate z-scores using the formula of xi, that is our specific value we want to locate on the standard normal distribution, minus the mean divided by the standard deviation. So a real easy example, if our value we want to test is 1059 for our SATs, 1059 minus the mean of 1059 is 0. 0 divided by 210 is 0. So we would be at the 0 point on the standard normal distribution. We can, of course, do this for our specific values that we've already located. If we have 1269 as a value we want to test, 1269 minus 1059 gives us 210. Divide that by our standard deviation of 210, and we are at positive 1 standard deviations from the mean. So once again, we can plug in any specific value we want into this formula along with our mean and standard deviation and locate ourselves on the standard normal distribution. So let's look at 1300. We can calculate the z-score for 1300 by subtracting 1059 from 1300. If we do that, we get 241. We divide 241 by 210, and that gives us a z-score of 1.15. So here, having that 1.15 z-score makes intuitive sense. If we know that we have 1269 at plus 1 standard deviations, we know that 1300 as a score is just above that score of 1269. So that corresponds to a 1.15 on the standard normal distribution. So once again, these z-scores simply act as a translation function to allow us to take any normally distributed variable and locate its values on the standard normal distribution by essentially setting our mean to 0 and then norming those values around our standard deviation.